You ever stop and think about the invisible tools that are shaping our world? I mean, from the phone in your pocket to the car you drive, there's this incredibly powerful method working behind the scenes, a way of seeing the future before it even happens. Today, we're going to pull back that curtain on one of the most important tools of the 21st century, computational modeling. So yeah, let's dive in. Okay, let's start with a really basic problem. How in the world do you safely study a shockwave from an explosion that literally lasts for a few microseconds? Or how could you possibly understand the insane pressure that's building up inside a volcano, miles under the earth? And what about stuff that's just, well, too big, or even physically impossible to recreate in a lab? The answer? You don't do it in the real world. You build a copy, a perfect digital twin where you can control every single variable. You create this virtual laboratory right inside a computer where you can run all the impossible experiments you want, safely and over again. So first up, let's just get on the same page about what we mean by a virtual laboratory. What does it actually mean to build an entire world inside a computer? Well, it's all about computational modeling. It's basically the art and science of taking the fundamental rules of the universe, math, physics, chemistry, and then using computer science to weave them all together into a simulation, a dynamic model of a real-world event or a system. And right away, this shows you a huge contrast. Real-world experiments, they're essential, of course, but they've got some serious limits. They can be unbelievably expensive, sometimes incredibly dangerous, or take years and years to run. Computer simulations, though, they just flip that script completely. They're safe, you can repeat them perfectly, and they can compress a decade of change into a few seconds. And maybe most importantly, they let us see things we could never, ever see with our own eyes. All right, now let's see this thing in action. We're going to look at some of the most extreme applications you can imagine. We're talking about modeling violent, energetic forces that are right at the edge of what we can even comprehend. So, researchers are using these digital labs to study stuff that's almost impossible to observe directly. They can model the exact way a shockwave travels from an underwater explosion, or they can see exactly how a warhead penetrates armor and breaks apart. They can even pinpoint the formation of these microscopic hotspots that actually trigger a detonation. You can simulate the insane impact of metals during explosive welding or the chaotic flow from a burst pipe. I mean, each of these is a whole world of physics, and it's all unfolding in fractions of a second. Now, a quote like this, yeah, it might look a little dense, but what's hiding in there is fascinating. What mechanical thermal chemical coupled really means is that the simulation isn't just looking at one thing. It's modeling the entire chain reaction at once. The physical impact, the intense heat that generates, and the chemical reaction, the explosion that follows. It's a complete, holistic picture of a violent event. And this is where modeling becomes a kind of superpower for understanding things. So take what happens when a shockwave smacks into a piece of metal. To our eyes, it's just instant, catastrophic failure. But a simulation can slow it all the way down and show us this hidden four-stage process. These tiny little voids form, then they grow, then they link up, and then the metal actually fractures. This turns a violent, chaotic moment into a predictable process. And that's the key, right? That's the insight you need to design stronger, more resilient material. But this technology isn't just for studying man-made forces. Scientists are using the exact same principles to model the biggest system we know, our own planet. The scale here is just staggering. We can build a digital twin of a whole volcanic system to try and predict its next move. We can simulate what happens when a volcano erupts deep, deep under the ocean. We can even analyze decades of temperature data to find patterns of explosiveness, which means rapid change. Some models are even trying to figure out the ancient, energetic events inside the Earth that might have created our moon. It's a way for us to ask the biggest questions we can think of. And here's the thing. These models aren't just theoretical. They are constantly being fed with real-world data. So, to predict an eruption, a model pulls in live information, the tiny earthquakes from seismic activity, the sulfur dioxide gas being released, the subtle swelling of the ground. It uses all of that to build this constantly updated picture of a super complex, interconnected system. And that same idea is being used in systems we deal with every single day. Okay, so we've seen the extreme and the planetary. Now let's bring this powerful idea down to a much more human scale and see how these virtual worlds are already shaping our real one. Because the truth is, modeling isn't just for things that go bang or for entire planets. Its greatest potential? Well, it might just be in understanding us. I mean, just look at this range.
In urban planning, models use live data from detectors to simulate traffic flow and actually predict traffic jams before they even happen. In economics, they analyze data to understand the complex links between things like economic growth and crime rates. Security models can even map out human relationship networks to help predict threats. And in medicine, well, as we're about to see, it's getting incredibly personal.
And this is just amazing. Doctors can now take an MRI scan of a patient and create a unique, one-of-a-kind 3D model of that person. Then, they can simulate a treatment like shockwave therapy on that digital twin to see exactly how it will work and fine-tune it for that individual before they ever even touch the patient. This is the virtual laboratory being used to literally personalize healthcare.
So where is all of this going? In this last section, let's look at how a new force is transforming these digital worlds and turning simulation into something that looks, well, a lot like prediction.
And this is where we're seeing a really fundamental shift. See, traditional simulation is based on the laws of physics. You build the rules, you push a button, and you ask, what if I do this? The outcome is determined by those rules. But this new wave is AI-driven. It uses deep learning to chew on decades of historical data. And instead of asking, what if, it asks, what's most likely to happen next? It's a huge shift from a world of what if to a world of what's probable.
And this isn't some far-off future. This is happening now. AI is being trained on massive data sets from oil fields to predict how much a reservoir will produce. Deep learning models are being fed thousands of simulation results to learn how to instantly predict how a shockwave will behave. And AI can now figure out the perfect parameters for a really complex process like explosive welding, which is something that used to take tons of trial and error.
It really all comes back to this. We started with a tool to help us see the invisible, the events too fast, too big, or too dangerous to watch. But by combining that tool with the predictive power of AI, we're building something else entirely. We're building a world where we can start to predict the uncertain. Which leaves us with one last, pretty crucial question. As this technology gets exponentially more powerful, if we really are getting to a point where we can simulate almost anything, from a single atom to an entire society, what should we be the most careful about predicting? What are the futures we should be wary of building, even if it's just inside a computer?